And thank you. It's great to be with you again and give another talk after maybe 2 years, I don't know. Since the last talk, I relocated to Edinburgh, but my accent is still Italian. I don't know if this is good or not. If you have troubles understanding me, please let me know, and I will try to slow down or speak more clearly. Okay. So I guess I should start. So this is typical intro slide to make you sure that you are in the right Zoom call. This is actually how the slide should have been in my head, but basically my partner told me that it wasn't serious enough, so I changed it. But anyway. Okay, so just 2 words about me. I'm Federico. I've been a database consultant and database administrator for a long time. Basically, I've been a database professional for 20 years. Well, let's, before starting, let's briefly say what this talk is and what it is not. It is not a tutorial about MariaDB, so I will assume that you know the basics of SQL. If you don't understand something, of course, you can ask and I will answer your questions. It is basically a talk about some cool features, in my opinion. Okay, so basically, I will talk to you about the Connect storage engine. In a moment, you will know what it is. About temporal tables and about using JSON data in MariaDB. In the process, we will also briefly see some other cool features that you may know or not, but they are minor features. So we will not talk a lot about them. Okay, so let's proceed. Okay, let's see how you can query remote data sources or heterogeneous data sources in SQL in MariaDB. First of all, why would you do that? Well, first of all, because it's SQL. So SQL is basically a small subset of English. So it's actually a very intuitive language and everyone can understand it. Also, you often happen to, well, I don't know if you do, but people often happen to import data from other data sources, which could include remote APIs or files or whatever. And also because you may want to interact with some data, maybe some databases, some files that are written by other systems that you don't have control on. For example, proprietary applications that maybe write data into an SQL Server database, and you don't have any way to touch the source code of those applications, but you still want to have those data in MariaDB. Okay, so let's see how it works. This feature is basically supported via a storage engine called Connect. What is a storage engine, first of all? Well, a storage engine is a plugin. is a type of plugin, because MariaDB doesn't really know how to write data or write indexes or read them or cache them. It delegates all these operations to a particular plugin type, storage engines. Normally, users don't even know about storage engines. They just use the default one, and that's totally fine in most cases. But a cool consequences of having storage engines is that storage engines should theoretically run queries, write data, but they could actually do anything. Okay, they could do something more creative than that. And we have some examples. For example, the black hole storage engine writes absolutely nothing. Black hole tables are empty. Why it is useful? Well, it is another topic. Let's not talk about these examples, but they exist. If you're curious anyway, you can run the command show engines in your MariaDB, and you will see which storage engines are supported, at least in your MariaDB version. Maybe some are not available because you may need to install some plugins, but still you will see what you have. So what Connect does is it treats generically external data sources as if they were local tables. Okay, so the idea is very simple. The idea is I create a table and I connect it to I don't know, a remote database or a local JSON file, and I will be able to use it as if it was a regular table. Okay. So which type of data sources are supported? Well, I kind of categorized them into three classes. Files, it supports CSV, JSON, XML, HTML tables that are part of a bigger HTML page, custom files, so you are able, for example, to read, I don't know, Apache logs, for example. You have to communicate to Connect how data is stored. You have to communicate to Connect how they are structured. And this is out of the scope of this talk, but you can do it anyway. And these files can also be in archives, in zip archives. Okay. Also, Connect can use tables from remote databases, and it can, of course, use the MySQL protocol, which is also MariaDB protocol. It can connect to MongoDB and use a collection as a local table, and it can connect to basically most other databases using ODBC or JDBC for Java databases. There are also some tables for some table types for data transformation, and I will mention these later. Of course, as you can guess, working with a remote data source can be slow, but if your purpose is to import data or export data, or if you just have to write a small amount of data once in a while and you don't care about performance, well, in all these cases, Connect is a very flexible tool that you can consider. So before doing anything with Connect, you will have to install it. To install it, in theory, you should run a simple SQL command, which is written here. If you get the error shown in this slide, it means that you don't have the plugin in your plugin dir. In those cases, you probably have MariaDB installed from Ubuntu repository or Fedora repository, and you have to install the dedicated packages to install Connect. This is also true if you use MariaDB in Docker using the official image. Okay, so in this slide, I show you an example. Okay, I will not show you an example of everything that you can do with Connect because it would take years. We only have 1 hour, but this example is relatively simple because we're just reading data from a CSV file. And you can see, first of all, that the syntax to create a table is very similar to the syntax to create a regular MariaDB table, but there are some more options that I've written in bold, okay? The first, most important, is engine connect, of course. And then we have to tell Connect which type of data we are going to work with, in this case, CSV. All other options depend on table type, okay? For CSV, we have these options and many others too. So if you're curious, look at the documentation. But some simple options are, first of all, the file name. Of course, the file name must be a file which is accessible by MariaDB. So if you're on Linux, you will have to give, well, there are two options. You give the file very loose permissions, or you make the MariaDB user the owner of the file, okay? Then, okay, by default, the separator character between the columns is comma, but in this case, for example, it could be a tab, okay? So I specify this. Block size is something that I will mention later. Is not super important, but it can be. We will talk later about it. As you can see, there are also column options. So for example, here we have a last modified column, which is a date, and we specify the date format, okay? So this is good because, you know, different programs export data with different date formats. So we may need to specify which format we're using. So here I show you how to basically copy data from the Connect table to a regular table. Okay, so this is the most simple case actually. We have a file, we create a table which is based on that file, and we copy data from the Connect table to a regular table. Okay, we can use a single SQL statement, which is insert select. We insert the results of this select. In this example, I added a where, but it can be useful in the real world because maybe you import data incrementally, like, for example, every time you import the last week. But I mainly did this to show you that you have all the power of SQL when you do this. So you could, for example, transform data. Also, I used insert ignore, which means if some rows are duplicated, meaning some rows already exist in the regular table, just skip them. If you don't write insert, well, the whole statement will fail if some rows already exist. Well, I don't want to dig too much into this, but MariaDB also offers other syntaxes to replace rows or to just update the values of some columns in the case duplicates exist. Anyway, let's proceed. Here I show, another example, but this is basically the case when we are creating a file. So if I go back with the slides, this is the statement we used to create the file. In this case, we were assuming that, sorry, the table, not the file. We were assuming that the base file exists, but we could also run the same statement to create a new file and then populate it. Okay, so as I show here, we can, in this case, we can run an insert, and then, well, this is basically a syntax which you can use if you're using the MariaDB command line client, which comes with MariaDB. You basically write exclamation mark, and then you can enter a system command, and you will see, and you will see the output without exiting MariaDB client. This is just a test to check that actually we have wrote one line into the file. Okay. We can also index the files. You will probably wonder, how is it possible? I mean, for example, if we want to import a CSV file, well, the file will only be data, okay? Where are the indexes written? Well, this is actually possible because indexes are written separately into separate files, okay? So the original file is not touched. You have a limit, a strict limit about the length of the indexes with connect. So it's important to define columns instead, I mean, specifying the column length and specifying the character set you are actually using instead of using the default, which is usually UTF-8. In this way, it is unlikely that you will hit the limit of the index length. And then, as I show here, you can use a simple alter table to create the index, as you would do with any other table type. In this example, I also show you that you can create a single connect table, which is a collection of several files. Okay, how does it work? Well, you create a separate connect table for each file, and then you create a table with table type TBL, which is, I think, table list. And then you list the tables that are part of this one. Of course, the files must have the same, well, the file could have different structures, but the connect tables you create must have the same columns with the same names and the same data types. Okay, this is useful because maybe you have to import massive data, and you are receiving several files. So yeah. You can also merge connect and non-connect tables. Okay, so for example, in the previous example, well, we had import product 1 and import product 2, which were two connect tables based on CSV files. But then suppose you also have this table called product, which is the regular table in which you want to import the data. Okay, maybe you do it on a regular basis, and to merge this table with the connect tables, you basically have to first create a so-called proxy table. Okay, it's another connect table type. So you specify the table name, the new table name, you specify engine connect, table type proxy, and then tab name, you specify product, because the proxy table is based on product. Okay, and then you will be free to create this new TBL table, which merges product, import product 1 and import product 2, and you will be able to run SQL queries on this big table, and the data will be read as if it was a regular table. What happens if you try to write into this table? Well, you can't. Simply because if you try to insert one row, MariaDB will not know in which file or in which table the row should be added. So it's read-only. Okay. It can be useful, for example, to make some checks on the data before importing them. Well, yeah, there can be use cases for this, actually. In this example, I show you how to create a table which connects to remote databases. In this case, it's an SQL Server database. So what I specify is, again, engine connect, table type ODBC, because I have to use an ODBC connection. Tab name, which is the name of the remote table. As you can see, it doesn't match the name of the local table, and it's perfectly fine. And then I specify a connection string. The syntax varies based on the database I'm going to interact with. In this case, it's the syntax of SQL Server. As you can see, I'm not specifying any table, any column name or column type. This is the easiest case. If possible, Connect will infer all the table names and types from the remote database. Sometimes it's not possible because, for example, SQL Server has some data types that don't exist in MariaDB, or maybe they are just called with different names. And in that case, you may need to specify all the columns manually. Okay, it's harder. It's typically a pain in the back, but yeah, it's doable. Here, I wanted to show you the last type of tables I mentioned before, which is table types for data transformation. There are three types of tables for data transformation. The first is pivot, which is probably the most typical because, well, I don't know if everyone knows what a pivot table is. It's usually a double entrance table, okay, where the first column can be seen as a list of columns, and basically every cell is an intersection between two columns. It's a two-dimensional table, basically. Some databases have a pivot syntax to basically visualize the results of a query as a pivot table, but MariaDB doesn't have that. So that's why it can be useful to use a connect pivot table. Xcol and occur are similar, except they are the opposite of each other. So Xcol basically normalizes tables where a column contains a comma-separated list of values. So, for example, in the left table, you can see that we have an imaginary table with two columns. The first contains nation names. The second contains a list of cities, and the list is separated by a comma, okay? Basically, this is not a complete example because we don't have the time, but with an Xcol table, you could obtain the right table, the table you see on the right, where basically each row is split into more rows, okay? So the comma-separated list is normalized and it becomes a set of multiple rows. Occur is the opposite. If we have a table which is similar to the right table, it can become similar to the left table. So rows can be merged and different values can become a comma-separated list. Okay, let's proceed. Oh, sorry, I left this by mistake. There is only one other thing I want to mention about Connect, because typically people ask me. Basically, when you create a Connect table which is based on a file, if the file already exists, the file is read-only. If you try to insert data, Connect will reject those data. If you run an alter table, the file will not be modified, okay? If you drop the table, the file will not be deleted. The table will be dropped, yes, but the file will not be deleted, because existing data is considered like precious, so they must not be altered. But if you create a table based on a file which doesn't yet exist, you can create the file. When you insert the data, the file is created and it's not read-only. Okay. Anyway, let's proceed. And let's talk about temporal tables. This is one of my favorite topics. I gave a lot of talks about temporal tables, actually. So what are temporal tables? Do not confuse them with temporary tables. They are something completely different. Temporal tables contain versioned rows. Okay, so whenever you create a row, for example, it will contain a timestamp which says when the row was created. If you update the row, a new version of the row will be created. The old version will have a new timestamp which says when the row version stopped existing, and the new row version will contain a start timestamp. If I delete the row, the last version of the row will have a new timestamp which indicates when the version stopped existing. Okay, but there are three types of temporal tables. The system version tables handle these timestamps transparently. So you don't need to worry about those timestamps. You can run your SQL queries normally. You don't have to use any special syntax if you don't want to. For example, if you run a select against a temporal table, you will only get, by default, you will only get the latest version of the data. Application time is different. You have to handle yourself the versions of the rows, okay? So this means that you can actually delete rows from an application time temporal table, but you can never, well, actually a database administrator has ways to delete historical data when they grow too much, but typically the application can't delete completely a row, okay? It will logically delete it, but the old version will remain visible when using a special syntax. We will see this briefly. The last type is actually by temporal tables. It's just tables that are both system versioned and application time, okay? So it means that every row has timestamps handled by MariaDB, which say when the table was physically, sorry, when a row was physically inserted or modified or deleted, and these cannot be affected by the application. But at the same time, the application will also be free to handle what's called application period. So basically, it will decide when a row is logically valid, okay? So in the example, I will only show you system version table. Okay, again, because we don't have enough time to talk about everything. If you're interested, you can find application time tables in the MariaDB documentation. Okay, so again, MariaDB automatically maintains the row versions for system version tables, okay? It handles automatically the start and end timestamps of each row, or it can handle, instead of timestamps, the transaction IDs. Why? Well, because, you know, MariaDB is a transactional database. So transactions can happen at the same time. The data modified by one transaction cannot be seen by other transactions. So for example, I could start a transaction now, I can delete a row, and I can commit my transaction, which means I will successfully end my transaction, for example, in 10 seconds. Okay. In the meanwhile, other connections could run some selects, and they will still see the row that I deleted. For other connections, it will only be deleted when I execute a commit of my transaction. So this means that if we only check the timestamps, well, we can see that, for example, a row has been deleted now from a logical point of view, but in practice, other transactions can still see it. So to debug some particular cases and keep into account the concurrencies and what other connections are seeing, well, we may choose to use transaction IDs instead of timestamps. But honestly, this makes everything more difficult. So in most cases, it's just not necessary, because, you know, if you do that, you will see, okay, this row version was created by transaction ID 100, and it was deleted by transaction ID 200. But when did this happen? Well, you can still find out when it happened, but it's much more difficult. Anyway, okay, let's proceed. Oh no, before proceeding, let me just highlight one thing. You probably know that MariaDB supports replication. Okay, so you can have a master MariaDB, and you can have some MariaDB replicas which replicate data from the master. An interesting thing is that you can have a regular table in the master, and you can make it a temporal table on the replicas or on some replicas, for example. And that's interesting because if you do so, you don't affect at all the behavior of the master. Maybe you can't, maybe you could, but you don't want to run a risk because you have some applications already using those tables. So for those purposes, you can use replicas, and in the replicas, you will see temporal tables. So basically, the master will do its work, and the replicas will contain information about when that the changes were made. Okay. If you don't understand something, again, please ask. I'm not checking the chat because otherwise I would lose my focus. So I hope that if there are questions, someone can just talk and I will hear the question. So in this example, I show a regular table. Okay, it's a table, for example, to handle tickets. In a ticketing system, for example, used by customer support. Okay, so we have, well, of course, an ID. We can have the state of a ticket, a brief summary, and a description. But once we have this table, we can make it a temporal table. Okay, so I will talk later about the first two options. The first thing to notice is we have to add some columns. Well, we don't actually have to. If we don't add columns explicitly, MariaDB will create invisible columns containing the timestamps of the various row versions. But I really suggest to create them explicitly, because if we do, we will be able to use these columns in our queries. And this will make our queries much easier. I will show you later why. As you can see, I also added a default for valid from. Okay, so when you insert a row, by default, it is valid from now. Okay, and there is also a default value for valid to, which is the highest possible value for a timestamp. Okay, so hopefully we will never reach this value. So it will always remain in the future. Then I can create some indexes containing these columns for performance reasons. And we have to use this syntax, add period for system period, because it's a system version table, and we specify the column names. And then we just write add system versioning. Maybe the syntax is a bit verbose, but it is what it is. And anyway, you do it only once. Okay. So once we have this, we can run some interesting queries. Okay. So for example, here, we select everything from the ticket table, and we will only see current data, because as I said before, by default, we only see current data. Okay. Also, we defined the timestamp columns as invisible. So by default, we don't see them. We don't get them in a query. Okay. In the second query, we specify that we want to see those columns. We specify asterisk, but then we specify the column names. So we will get them into the results. But it is not very useful yet. The next query is more useful because we also add for system time all. So this means in this case, we will get all the row versions, including the rows that have been deleted. Okay, but we specified that we want to get the timestamps inserted at or deleted at. For each version, we will know when it started to exist and when it stopped to exist. Okay. And then here I show you, for example, a query to get the row versions that don't exist anymore. In the comment, I wrote get deleted queries. It is not 100% correct. They could be rows that have been modified. Okay, so we just specify this syntax, which says, okay, from the lowest possible timestamp value to now minus 1 microsecond. Okay, so everything basically that doesn't exist anymore. But as you can see, I'm using a special syntax here, right? This syntax has been created for this purpose. Okay, you can use it if you like it. But what I don't like about it is you have to learn it. Instead, you can use the second syntax, where we basically only specify a where clause. Okay, we specify where deleted at less than now. What is the benefit? Well, we just write plain SQL with a small addition, which is for system time all. But theoretically, you could use an ORM and still be able to compose these queries. I only talk about SQL. I don't talk about ORMs. I don't talk about PHP. So I don't know, for example, how you can add this small syntax for system time all, but hopefully a good ORM will provide a way to do so. Okay. But again, we can do this because we created the timestamp columns explicitly. If we didn't, well, we couldn't use the second syntax. Sorry. With this query, we can see the history of a particular row. Why is it useful? Well, for example, for debugging, or maybe because we want to know the history of a particular ticket, because maybe a customer is complaining. So we specify the column we are interested in. We specify where ID equals blah, 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 and we specify order by deleted at, and the rows will be, the row versions will be ordered chronologically. Very simple. And here I show you how to read a row from a specific time, from a specific point in time. If you want to use the special temporal table syntax, you can use the first version of the row for system time as of timestamp. But again, it's not necessary. You can write a regular query with a normal where, in this case, where ID equals number, and date between inserted at and deleted at. So basically, this date will be greater than inserted at and smaller than deleted at. Okay. And well, this is a bit more complex, but not too much if you understand it. Basically, we run a join, an SQL join between a table and itself, but specifying two different points in time. Okay. I would not, I mean, if you want me to describe every part of the query, ask me and I will do it. But anyway, I think that the basic idea is understandable. Okay, so we specified the table name 2 times with 2 different aliases, T1 and T2. For T1, we specify this time condition. Okay, this date. And for table 2, we specify this time condition with this other date, 1 month later. Okay. We specify also, of course, that there must be a match. Okay, so the ID in table 1 must be the same as ID in table 2. Okay. Okay, these were, of course, just examples. You can do many more things with temporal tables. For example, you can do statistics about rows that were added or deleted by year, by month, by weekday, by daytime, or whatever. Okay. This is useful, for example, if inserted rows represents maybe a new sale or a new user who registered the website. Okay. You can run statistics on the length of rows' lives. So, for example, in the previous case, it could be useful, I guess, because it would be the time taken for the ticket to change the state. Okay, so first it's opened, then it's approved, and you can see how much time this takes. You can get the rows that never changed for some reason. maybe just for debugging, for example. You can do some kind of anomaly detection. For example, you can see rows that have been modified or deleted at strange times, or maybe rows that are modified too often. And of course, you can examine the history of a specific row to find problems. Again, it could be debugging because maybe your application has a bug and changes some rows in a way that it shouldn't. Or maybe it could be to find out if a malicious user did something wrong with your database. Okay, maybe someone got access to your database and made some evil changes. I don't know. Okay, so this was the last slide about temporal tables. Let's talk about JSON. I'm continuing to talk because I didn't get any question yet, which I didn't expect, honestly. So again, if you have something to ask, feel free. Just interrupt me. It's totally okay by me. So, JSON use cases. Why would one put some JSON into a relational database? This is a question that I'm asked sometimes. Well, there are actually many reasons. Maybe you want to build a prototype application. Many people told me that they use MongoDB because it's flexible, it's schemaless, so you can easily build prototypes even if you don't know in advance which columns you need. And okay, sounds probably reasonable, but in most cases, you know which tables you have. You just don't know all the columns probably, so it makes sense to use JSON, to insert JSON in some tables to build a prototype. Or maybe you store data in an intermediate form, data that must be imported or exported. Or maybe you need to store data that is nested in very complex ways. Or you have heterogeneous data in a table. We will see an example in a moment. Or you can store arrays, lists, sets, because some databases support arrays, but MariaDB doesn't support arrays. So in theory, this is a limitation, but in practice, you can store a JSON array in one column. Or you can store key values pairs in a column. Okay. If you know the set or enum types, they are kind of obsolete. They only exist in MariaDB and MySQL. So using a JSON object instead could be a good idea. Okay, so let's see an example. Suppose we have a table which is not a table, one step back. Suppose we need to store somehow a catalog of products for an e-commerce. This is a typical example. What is the problem? The problem is that probably we have products of different types with different characteristics, but the characteristics are not completely different, okay? So for example, all products maybe have a name, a description, and a price, but maybe you have shirts which also have a size and a color. If you sell, I don't know, pens, well, they don't have a size, of course. But then maybe you store fonts and this is tricky because you have size, but it's not the same size, okay? A shared size is something like S, M, L, but a font size is probably in centimeters or in inks. So, and then you have maybe brand, model, weight, whatever. So how do you store all these different data in a relational database? Well, this is kind of an open problem. No solution is really perfect, but JSON is relatively, it's almost perfect, I would say. Sorry. So let's see the solutions anyway. The first is you can have a single table with a column that every column is a property that at least one product has. This is terrible, right? Because you will have a very large table. It will look like an Excel document because, I mean, most columns will probably be only used for a small subset of products, not for all products. In all either cases, they will be null. And having very big tables can be a problem because, I mean, when you want to repair a table because maybe it's damaged, it's corrupted, physically corrupted, it takes more time. If you have to take a backup, it takes more time. If you have to add a column, you have to make a change on a very big table. An alternative is, well, you can have a different table for every product type. But this is also not very practical because maybe you want to get the product with the highest, the maximum price, for example. You can do it anyway if you know SQL union statement, but it's more difficult, it's slower. I mean, it's not good. Another option is having a common table with columns that are useful for all the products, and then having a separate table for each product type, containing only the columns that refer to a particular product type. Yes, you can do it, but I guess it's more complicated for a developer. It's not really an elegant solution. But now that JSON is supported in MariaDB, like most databases actually, you can have a JSON column. Okay, so you can have a table with the columns that are needed by all products. And then you can have a JSON column for the columns that are needed only by some products. Okay, so for example, if you add a new product type, you will not have to add a new column into this table. Okay, so it can be very practical, but there are some problems. So let's see how we can do this in practice. Okay, this is only one example, but it's probably the most common, and anyway, it's useful to show some interesting things that we can do with JSON data. So in this example, I create a product table with the columns that are common to all products. Then I have these attributes column of type JSON, a unique index. Okay, cool. Apparently cool, but there is a problem. Suppose I want to get the list of available colors for for shirts. Okay, well, what I have to do here is this. Sorry. Okay, what I have to do here is this. I specify, well, type equal shirt, all good so far. But then I have to I have to add a condition on the size property. Well, there is a missing quote, sorry about it, but anyway, the rest of the query should be correct. How do I do this? I use the JSON extract function, specify attributes as a JSON argument, and then I specify a JSON path argument, which is size. What is the problem with this? Well, it's verbose, and yes, this can be a problem actually because it makes queries more difficult. But most importantly, this is slow, okay? Because MariaDB will have to look into all these JSON documents and look for a size property. So what can we do? In theory, we would like to add an index on the size property, okay? And since we have this distinct clause listing different colors, ideally the index should also include the color property. So can we do it? Yes, we can, with some more work actually. So what are we doing here? As you can see, there are two more columns written in bold. They are generated columns, okay? I didn't include the complete syntax for brevity. I didn't specify the type. So if you try to run this query, it will not work, but it doesn't matter. I only want you to understand the idea behind this. The syntax, well, you can check it in the documentation. So what I say is the column is generated always as, and then I put an SQL expression. Okay, so every time I insert a row or modify a row, MariaDB will calculate the result of this SQL expression. Stored means that the column is physically written to the disk. In this case, it's necessary. Anyway, the SQL expression is simply JSON extract, and I pass this JSON path, this simple JSON path. Okay, so one column will contain the color property from the attributes JSON, and the other will contain the size property from attributes. And then, once I have these columns, I can create an index on them. Okay. So I can't index JSON data directly, but I can create generated columns containing the data I'm interested in, and then I can index those generated columns. And my queries will be fast if I do it properly. I will briefly mention some other typical DBMS's features that it could make sense to use with JSON. And this is probably interesting because, I mean, okay, we are working with a relational database, we are putting some JSON in it, but this doesn't mean that the data is not validated. We can still validate the data somehow. So for example, in this case, I'm using this check clause. I don't know if everyone knows check. It's just a syntax which means for each row that is added or modified, check if this expression is true. If it is not, return an error. Don't insert the new row. Okay, so in this case, I'm just saying that the color must be black or white or blue. Okay. I can also create unique indexes, but in most cases, I will have to do something more complicated than usual. Okay, so for example, in this case, I want to create a unique index on model and color, but only for the fonts. Okay, why? Because other products type maybe don't even have color, or maybe for other products type, this unique index doesn't make sense. Okay, so I generate this, I define this generated column based on this expression, which is if type different than font, return null. Why is it useful? Because a unique index allows to insert any number of nulls you want. Okay, you can have many nulls, but you can have only one occurrence of every other data. Okay, so only in the case where the type is font, I will this expression will be calculated, and it's basically concatenate with separator. Okay, separator is a dot in this case, and the result of this expression will be the name of the model of the font plus the color. And in this way, I can have, for example, a font of a certain model which is black, but it must be exactly one or zero, no duplicates. Okay. I wanted to mention that if you like foreign keys, you can actually use the same logic to define foreign keys, but well, I'm not really a fan of foreign keys for many reasons, because they reduce scalability. They make it impossible to do certain modifications on tables without acquiring a lock, so they are a problem in production. So yeah, I will not dig into this, but if you understood the logic of using generated columns on JSON data, you will be able to create a foreign key. Okay. Okay, so this was the last topic.